Hi, welcome back everybody. We are still in chapter 5, but moving on to our next section, which is section 3. Title says at the top, polynomial functions. So just even going back to basics here with polynomials, the definition at the top, if you have a polynomial in one variable, that just means you have a polynomial with one constant or consistent variable. Okay, so basically you have all x's in your polynomial, or all y's, or all a's, whatever the variable may be, but that variable stays constant in each and every single term. So there's even some examples that you see in the next part, but there's two ways to name your polynomial. The first way in this box is naming it by the number of terms that you have. So as you can see, if you have one term, and there's an example on the right, if there's only one term, like 2x squared, then that's called a monomial. So we've kind of talked about this. Let me use my highlighter. So again, we got monomial if there's one term, binomial if there's two terms, and the example to the far right is x minus 4, so that's two separate terms, minus sign separating the two terms in between. Trinomial means you have three terms, so tri means 3. So as an example, x cubed minus x plus 1. Again, there's three separate terms. And then if it's 4 or more, then we just say that it's a polynomial. So there's really no special name if there's going to be 4 or more terms. It's just simply polynomial and that's it. So mono for 1, bi for 2, tri for 3, and then polynomial if there's 4 or more terms. And again, just to kind of recall, how do you find the degree of a polynomial? So the second way that you name your polynomial, besides the number of terms, is you also name it by the degree. So how you find the degree of a polynomial, it's going to be the degree of the monomial. So we learned this even back in section 1. It's the degree of the monomial with the highest or greatest degree. And that will determine the degree of the entire polynomial. Okay, so again, there's special names here. It's a constant if your degree is 0. So constant, again, let me get my highlighter back. Constant, degree 0. Linear is degree 1. So again, there's examples in the middle column. So a constant is just a number by itself, like -9, where you don't have an x, there's nothing to it. But the degree would technically be 0 since there is no variable. The degree would just be 0. And then linear, technically, again, this is going to be x to the first power, so the degree would be 1. And then x squared, that's called a quadratic, which we focused on all in chapter 4. Quadratics are degree 2. Cubic means you have degree 3, so the highest degree would be 3. Quartic if it's 4, and then quintic if it's 5. After that, we just simply say degree 6, degree 7, degree 8, degree 9. There's really no special names after that. Okay, but again, just looking at your degree, the highest power that you see, 3 is cubic, 4 is quartic, and then 5 would be a quintic. All right, the leading coefficient, what this is, it's going to be the coefficient. So coefficient means it's that number in front of your variable. That's what a coefficient is, but it's the coefficient of the first term of a polynomial in standard form. So it has to be in standard form in order to properly identify your leading coefficient. So that's going to lead us into our next definition. What is standard form? How do I know what standard form is? Well, you want to make sure the exponents, they should be going down in descending order. So exponents should be in descending order. So highest exponent first, followed by the next highest, followed by the next highest, all the way down until where you have actually no exponents. So as an example, let me just go back up here. I'll highlight this one. Let's use a different color. I'll use blue. So this right here, that's a polynomial in standard form. Again, you got your highest exponent first, followed by your next highest, next highest, next highest, all the way down to where you have your constant at the very end of -1. Okay, so I'll give you guys more examples. We'll get used to also writing these in standard form ourselves. But here is also a polynomial that's in standard form. Okay, so let's practice putting this all together here. Leading coefficient, that's the number again. That's going to be the coefficient of the first term of a polynomial in standard form. But like I said, this is already in standard form. You got your highest exponent, then your next highest, then your next highest, all the way down to where you have no exponents. So leading coefficient, number in the front, That'd be 3. So that's my leading coefficient. Let's see, the degree of this polynomial. So again, it's just whatever the highest monomial is, which would also be 3. So this right here, that would be my degree. Maybe we should label all this stuff. So this is my degree. This right here, I'm just going to abbreviate it LC for leading coefficient. But the degree of this polynomial is also 3. How many terms do we have? So if you just count it out, we have 1, 2, 3, 4 terms. So there's 4. So now we want to actually name it. So again, the 2 ways you name it by the number of terms, and you also name it by the degree. So based on the degree, it's definitely going to be a cubic. So it's degree 3. And as far as the number of terms go, there's 4 terms, so it's a cubic polynomial. Since there's 4 terms. So again, using those 2 names, that would be it. Cubic polynomial. So next part, we're going to do the same thing. We're going to rewrite these to be in standard form if we need to, and then identify each of the following. So part A, what's the leading coefficient? Part B, what's the degree? Part C, the number of terms, and then part D, name the polynomial. If it's not a polynomial in one variable, then explain why. Okay. So this next one, putting this guy in standard form. So highest exponent should be first, so that's x cubed. So positive x cubed plus 2x squared minus 7, now it's in standard form. So now part A again, leading coefficient, that'd just be 1, because it's a 1x cubed, so 1. Part B, the degree of this polynomial would be 3, so that's the highest exponent, so that'd be 3. Part C, how many terms do we have? There's 1, 2, 3 terms, so 3. And now part D, now we have to actually name this guy. Okay, so again, from the degree, and also from the number of terms, we would say that this is a cubic trinomial. It's cubic because of the degree 3, and it's a trinomial because there's 3 terms. Okay, that'd be it. All right, and this is actually going to be, this is a polynomial in one variable because there's only one variable all throughout the polynomial. Okay, next one. So technically, this is already in standard form. We don't have to adjust anything. It's already good to go. So looking at my looking at my degrees, you got the highest one first, the next highest, all the way down to degree 1. So when you have more than one variable like we do here, you want to basically base it off of the first variable. So when you have more than one variable, they should be listed alphabetically, A before B in the alphabet. So looking at just your A's, okay, you want to go from there, make sure those are in descending order. Highest exponent, next highest, and then you look at the B's next. Okay, so now, again, it's already in standard form. So part A, what's my leading coefficient? That'd be 6. Part B, we want to say the degree of this polynomial is part B, so that'd be 3. Part C would be, for this one, part C is the number of terms that we see, so there's 3 terms again. So if I had to actually name this guy, part D, this would be, again, a cubic trinomial. So cubic tri. But this is not a polynomial in one variable, because the reason why, you got A and you also got B together. So it's not a polynomial in one variable, it's a polynomial in 2 variables, but we could still go through the process and name it and everything else. Okay, so the next one, number 3. So first we write this in standard form, look for your highest exponent. That'd be negative 8, x to the 6th should be first, plus 3x to the 5th, plus 2x squared minus 4. So if you have missing terms, I can even kind of backtrack here. If you have missing terms, you don't want to fill them in. Okay, just list out what do you have for this problem. That's it. Okay, because you don't want to put in extra terms that you don't really have in the problem. But for this one, so part A, leading coefficient is negative 8. Part B, the degree, would be 6. Part C now, how many terms do we have? There's 4 terms. And now for part D, we want to actually name this guy. So again, based on the degree is 6. So there's really no special name. It stops at 5. 5 is a quintic. So we're just going to say that it's a degree 6. And then based on the number of terms, there's 4 terms. So that's just going to be a polynomial. So again, really no special name. Again, monomial is 1, binomial is 2, trinomial is 3. So 4 terms, 4 or more terms is just going to be a polynomial. And the last one, write this in standard form. So just switch these 2 around, be x cubed plus 8. So part A, leading coefficient is 1. Part B, the degree would be 3. Part C, the number of terms, there's only 2. And now part D for this one, well, based on the degree, it's a cubic again. Degree 3 is a cubic. And then, because there's only 2 terms, it's a binomial. So cubic binomial is the proper name. All right. So moving on to the next page. Over here, we got polynomial function at the top. So definition of this, it's just going to be a continuous function, which we're really not going to be seeing until after this page, but it's a continuous function. So we know what it means to be continuous. It means you have an infinite number of elements in your domain that can be described by a polynomial equation in one variable. So we're going to be starting to graph these polynomials. Again, last chapter we focused on quadratics. So this chapter we're going to be graphing all these different kinds of polynomials. So a cubic, a quartic, a quintic. We should know how to be graphing those at the end of this chapter. But going back here, we got 2 polynomial functions. We have these 2. So we got p of x and we got r of x. Find each value. So this is something we've already done before, right? So if you wanted to find p of 8a, that just means you're going to take 8a, plug it in everywhere you see an x into p of x, because you got that p out front. So if you plug in 8a, you would have, so p of 8a is going to be 3 times 8a squared minus 4. Okay, so you plug it in. Now, next thing, exponent. So you want to actually square this 8a, where you want to square both terms. So you're going to have 3, that'd be 64a squared minus 4. Next, multiplying 64a squared, that's 192a squared minus 4, and that's about all you can do. So you can't do any more. You can't actually subtract 4 from that, so that would be it. And then for b, same thing, but now we're switching over to r, because it says r of a squared. So you want to plug this in for r now everywhere you see an x. So if you plug in a squared, what you're going to have, you'll have 2a squared squared minus 5a squared plus 1. So plug it in everywhere you see an x. So now to simplify it, you would have, so the a squared squared would be a to the 4th minus 5a squared plus 1. And that's about all you can do. Again, you can't actually simplify any further. That would be your final answer. So the next one, now we're plugging into r. We're plugging in x plus 2. So everywhere you see an x into r of x. And this one's a little tricky, so let me make sure I go through this one in detail. So everywhere you see an x. Okay, so big problem here. All right, first thing, exponent. So you want to square the x plus 2. But to square a binomial, again, you have to FOIL x plus 2 with another x plus 2. Only if you have a monomial like we had for the previous problem can you just use the laws of exponents. Okay, that only works with monomials. But with a binomial, you have to actually FOIL this out. So when you FOIL x plus 2 with x plus 2, you still got that 2 out front, but FOILing that would give you x squared plus 4x plus 4. And I'm going to go ahead and distribute here negative 5 to both terms, so minus 5x minus 10 plus 1. And now distributing the front, so 2 to all 3 terms would be 2x squared plus 8x plus 8 minus 5x minus 10 plus 1. And now combining like terms, so 2x squared is on its own, but we have 8x minus 5, so that's 3. And then 8 minus 10, well that's negative 2, plus 1 be negative 1. So there's my final answer. Okay, the last one, same idea. See if I can squeeze this in here. But you have that 5 in front. That means you're going to be multiplying 5 times p of x plus 2. So first, let me just plug this in. Plug in x plus 2 into p. So when you plug that in, you're going to have 3 times x plus 2 squared minus 4. Okay, so again, FOILing out x plus 2, we just did in the previous problem, you will get x squared plus 4x plus 4 and then minus 4. Now distribute 3. So I'm going to have 3x squared plus 12x plus 12 minus 4. 12 minus 4, I get 3x squared plus 12x plus 8. Now, so we did p of x plus 2. Now we have to times this whole thing by 5. So now is the time to put that 5 in the front. So multiplying my final answer here by 5 would give me 15x squared. And then 5 times 12, that'd be 60x plus 40. And that is my final answer. All right, so I'm going to just kind of skip around a little bit now, just to make sure we get enough practice. But the next one, so p of negative 3, you're just plugging in negative 3 for x, so that should be easy enough. So p of negative 3 would be 3 times negative 3 squared minus 4. So that's 3 times 9 minus 4, so 27 minus 4. And you should get 23. There you go. The next one. So r of 4, you're plugging in 4 everywhere you see an x into r of x. So that would be 2 times 4 squared minus 5 times 4 plus 1. So plug it all in. So again, exponent comes first, 4 squared. That's 2 times 16 minus 20 plus 1, 5 times 4. 2 times 16, that's 32 minus 20 plus 1. So 32 minus 20, that's 12. 12 plus 1, you get 13. Okay, I'll just do one more here, just for good measure. So let's just do g. This will be the last one. I know we pretty much did all of them anyways. But for g, again, you're doing 2 times r to the negative 1. 2 times r to the negative 1. So first, find r to the negative 1. And then once you have that answer, you're just going to times it by the 2 in front. So r to the negative 1, that's going to be, so plugging this into r, you'd have 2 times negative 1 squared. And then minus 5 times negative 1 plus 1. So this would just be, again, exponent first, 2 times positive 1. Negative 1 squared is positive 1. This would be plus 5 plus 1. So 2 plus 5 plus 1, 7 plus 1, you get 8. But now, again, times it by the 2 in the front. So 2 times 8, and then you get 16. Okay, for h, I'll just kind of throw the answer up here if you want to practice one more time. What you should get is 9c squared minus 12 is your final answer. This last one, this big doozy, before we get to the story problem. Okay, this would be something that's probably more so like an extra credit question, but you only have one function, g of x, right? This is what you're doing to g of x. So starting off with, you kind of just want to put it, like piece it apart and then put it all back together once it's all said and done. So I'm just going to do this first part. Okay, g of 5a minus 2. So I need to plug in 5a minus 2 everywhere I see an x. So I'm going to have 5a minus 2 squared minus 5 times 5a minus 2 plus 8. Okay, so just doing again this first part. That's all we're doing right now. So binomial squared, 5a minus 2. Again, you've got to FOIL that with another 5a minus 2. And then I'll go ahead and distribute here. Might as well while we're at it. So that would be a minus 25a plus 10 plus 8. Okay. So foiling those two together, you would have 25a squared. So then you'd have minus 10, so minus 20a plus 4. So after I FOIL, this is what I get. Minus 25a plus 10 plus 8. So I would have 25a squared. Negative 20a minus 25 is negative 45a. And now 4 plus 10, 14, plus 8, that gives me 22. Again, and that's just the first part. Okay, so after we do g of 5a minus 2, this is what we have. Okay, so now we have to do the second part. I'll do a different color. So now we have to do this. Once we have that, we're just going to add them. Once it's all said and done, then we're good to go. So 3 times g of 2a. So first, just do g of 2a. Once you have that, times it by 3. So plugging in 2a everywhere you see an x, you would have 2a squared minus 5 times 2a plus 8, which would be 4a squared. This would be minus 10a plus 8. Okay, so I did the 2a part. Now, times this all by 3. So that would be 12a squared. That would be a minus 30a plus 24. And now I'm just going to add this with this one over here. So again, there's that plus sign in between. So if you add these two together, that'll be your final result. So I'll change my color one last time. So if you add those two, so we're doing the 25a squared, we're adding 12a squared, so that's 37a squared. The a's, so we got negative 45 and then minus 30, so that'd be negative 75a. And now 22 plus 24, so that would be 46. So plus 46. And there's your final answer. All right, there's the whole entire thing. So like I said, that'd be probably more like an extra credit question. Pretty fancy, all said and done. There you go. Okay. Last one, application. So it says the volume of air in the lungs during a 5-second respiratory cycle can be modeled by using V of t, where V is volume and t is time in seconds. Find the volume, it says, of air in the lungs 1.5 seconds into a respiratory cycle. Okay, so they give me this much. We know it's 1.5 seconds. They tell us, though, t is time in seconds, and that V is volume. Well, we're finding, it says, find the volume. So you're solving for V given t. 1.5 again, that's a time in seconds, 1.5 seconds, that's your time. So just plug in 1.5 everywhere you see a t. That's it. You're basically trying to find V of 1.5. So you're plugging 1.5 everywhere you see a t. So negative 0.037. And then you're doing 1.5 cubed plus 0.152. And then that would be 1.5 squared. And then plus 0.173 times 1.5. So obviously we got calculators to help us. But going through the process, simplifying along the way, start with your exponents. So cube this, square that, multiply by the numbers in front. Simplifying, you should get what I got is 0.476625 is what you get for your volume. Doesn't really give us the units though, right? So we're talking about volume. We could just say units cubed if we wanted to, or cubic units. Units cubed, cubic units, that'd be the volume. All right, so moving on now to the graphs. So today we're going to be doing just the basics of graphing, okay, just the basics. So we're not going through all the details of how we graph these, not just yet. We'll get to that eventually, but just basics. Basically, we're trying to figure out what do these graphs even look like overall. So you have constants, which would be just degree 0. So a function, keep in mind, these are all going to be functions. So if these are functions, that means they pass the vertical line test, each and every single one of them. Okay, so they're all going to be functions. If it's degree 0, if it's just a constant, that's just a flat line. So just a straight across horizontal line, again, that'd be it. Linear means you have degree 1. So even if you have something like degree 1 would just be y equals x, okay, or y equals 2x plus 3, or y equals 1/2 x minus 5. Those would all be linear functions, but that's just going to make a line. There's a straight line going up from left to right. So again, that's a function. Quadratics, degree 2, so that'd be like y equals x squared. That's just going to be a parabola. Okay, so we should know that an x squared function makes a parabola. So it makes that U shape. Okay, if it's going to be a cubic, okay, but now we have a cubic function, so cubic means you got degree 3. This is something new now, so we don't know about cubic functions. So we're talking about a degree 3 polynomial. A cubic function looks a little something like this. Okay, where it kind of starts down and then it curves its way up. Okay, next we have a degree 4, which is a quartic. So that'd be like y equals x to the 4th power. So x to the 4th power, again, there could be a lot more to that. It could be x to the 4th, you know, minus 4, x to the 4th plus 3x cubed plus 2x squared, keeps on going on. But it looks a little something like this. This would be a quartic. So starting up here, it's going to kind of loop itself around up and down. So it's almost kind of like two parabolas, if you think about it. And now we're moving on to a quintic, so that's going to be y equals x to the fifth power. So pretty similar to the cubic, but now, so starts off the same way, starting down here in this quadrant, it's going to loop itself around, up, and then back up again. That would be something similar to an x to the fifth power. Okay, let me fix this one actually, 'cause that's way too similar to the other one. So go up, come back down, go up again, come back down, and then go back up. So that would be more so like an x to the fifth power. Okay, which I'm going to explain this all and break it all down for you guys a little bit later. Again, we'll get into all the details and everything, but one thing I want you to notice is that if you have an even degree, so even, so like a quadratic, x squared and x to the fourth, on both sides, you see it's facing up on both sides. On both sides, again, it's facing up, facing up. Okay, these will always have the same direction on both sides. Whereas if it's going to be odd, like you see here, so degree 1, so this is x to the first power, you got odd, you got odd. On both sides of the function, they're going in opposite directions. So this side's facing down, this side's facing up, this side's facing down, this side's facing up, this side's facing down on the left, this side's facing up. Okay, so that's going to help you to try and determine exactly how these graphs are going to work. So even again, same direction, odd functions, they always have opposite directions. Okay, which leads us into, we're talking about this thing called M behavior, which is what I'm trying to illustrate to you guys up above. So it's just describing, it's a description of the end value of a function as it approaches positive infinity and also as it approaches negative infinity. So it's basically just saying, what is the graph doing? Okay, as my x's approach positive infinity, as my x's approach negative infinity, what is the graph actually doing in itself? So starting off, these first two, you can see it says leading coefficient is a positive number. So it says that a is going to be greater than 0. So again, that just means that you have a positive leading coefficient. So the LC is going to be positive. So here are some examples. Let's just keep it simple. So we got odd degrees. So my highlighter again, we got odd versus even. Okay, so keep that in mind, odd versus even. If it's odd and you have a positive leading coefficient, so let's just say y equals x cubed. Again, my quick description, my quick graph that I would have looks a little something like this. This would be an odd function, a cubic. Okay, now you want to actually describe what's happening. Okay, so as your x's approach positive infinity, as your x's go to the right, as x's approach positive, your graph is pointing up, which means p of x, which is the polynomial function, is also approaching positive infinity. Okay, but as your x's approach negative, so as my x's decrease backwards, my graph is pointing down. So this would also be approaching negative infinity. Okay, even degree. So if it's going to be even, so here's the graph of an even function. Again, let's just keep it simple. Let's just say y equals x squared. Keep it simple. Okay, here's my graph. Here's my parabola. So as my x's approach positive infinity, so as my x's are going to the right, positive infinity, graph is pointing up, positive infinity. As my x's approach negative infinity, so as my x's decrease, go backwards, my graph is still pointing up. So it's still going to be positive infinity. Okay, so that's when you have a positive leading coefficient. Keep that in mind, it's positive. Because now we're going to do the flip side. If your leading coefficient is negative, so if a is less than 0, so leading coefficient a is less than 0, that means now again you have a negative LC, negative leading coefficient. So what's going to happen if you had a negative leading coefficient? It's basically going to reflect the entire graph. So if that was positive right above it, still talking about an odd degree, now it's just going to be backwards. It's going to be reflected over the x-axis. Okay, so now you're going to have different M behaviors too. As x approaches positive, as my x's increase, my graph is pointing down. So it's going towards negative. As x approaches negative, as my x's decrease backwards, my graph is pointing up towards positive. Okay, and then same thing over here with my parabola. So let's just say again, I have a negative leading coefficient. Now it's going to be reflected over the x. So it's going to be facing down, which means for my M behavior, as my x's approach positive, my function p of x is pointing down towards negative. As my x's go back to negative, graph is pointing down, which is also negative infinity. Okay, so use this chart at any point in time that you need to. When you're working on your homework, anything, this is going to help you guys out when it comes down to it. Okay, when it comes down to finding these end behaviors, it kind of helps make a quick sketch of the graph too, to just get a better idea as to what you're looking at. But again, if you know that odd go in opposite directions and even always go in the same direction, so again, looking at your end behaviors for the even, they're always pointing the same direction. They're either both up, both positive, or they're both going to be down. So both negative. Whereas with the odd, they're going to be opposite. Positive, negative, or negative, positive. Those are your only options. Okay, but it all depends on that leading coefficient. If the leading coefficient is going to be positive versus being negative. All right, so let's put this all together here. So number 7. Leading coefficient is positive, positive 2. The degree, it's odd, so it's 5. So now label the end behavior without a graph. Well, the fact that it's odd, I know it's going to be opposite. So one's going to be positive, one's going to be negative. I know they're both going to be infinity. But now which one's what? Well, the fact that it's a positive leading coefficient, that means, again, if I just kind of make a rough sketch, I know it's going to be facing down here and then ending pointing up. So that means, again, as my x's approach positive, as x's increase, graph is pointing up, which would be positive infinity. And then as my x's decrease and go backwards, graph is pointing down, which is negative infinity. Okay, so for the next one. Leading coefficients, -3, degree is 2. So now we'll label the end behaviors. Okay, well, we have an even degree this time. So that means we're going to have the same end behaviors. So I'll just go ahead and put my infinities down here. But are they both going to be positive or both going to be negative? Well, that depends on your leading coefficient now. So again, if I make kind of a quick sketch here, since I do have a negative leading coefficient, both sides should be facing down. So that means, if I fill this in, negative, negative. Both sides will be facing towards negative infinity. Whereas the last one, leading coefficient, -4. The degree is odd, it's 7. So the fact that it's odd, again, you're going to have opposite end behaviors. So go ahead and write down your infinities, but are they positive or are they going to be negative? Well, again, that comes from now your leading coefficient. So they should be opposite. The way this one works, it's actually going to start facing up, but it's going to end facing down. So it's just the opposite of number 7. Okay, so if I label this as my x's approach positive, my function actually goes to negative. As x approaches negative, my function goes to positive. Okay, so just the opposite. Now, doing pretty much the same thing, but now we're actually going to be labeling it as an odd or an even degree and then a positive or negative leading coefficient. So let me kind of set this up. So again, we're going to first be doing the degree. So put degree all the way across. So determine, is it going to be even or is it going to be odd? And then the leading coefficient, the LC, is going to be positive or negative, which is always the harder part. The degree is usually pretty easy, odd or even, but the leading coefficient is a little bit tougher. So again, you're looking at the end behaviors for the first one. Both sides are facing down. So since they have the same end behaviors, I know it's going to be even. So let's do the next one. Okay, even or odd? Well, this one's facing down, this one's facing up. Since they're opposite, it has to be odd. The next one, they're both facing up, so it has to be even. And the last one, opposite. One's up, one's down, so this has to be odd. Now determine positive or negative leading coefficient. Okay, the first one. Since both sides are facing down, it's going to be a negative leading coefficient. So if both sides are facing down, that's what you'd have. And here's how I think about the odd ones. It starts off facing down, right? But then it kind of goes up, down, and then it ends pointing up. To me, that makes it positive. So if it's ending by pointing up on the far right side, that's a positive leading coefficient. Okay, whereas the next one, it's even and both sides are facing up, so that makes it easy. It's definitely positive. And the last one, it's just the opposite. It's flipped around from the two previous ones. So if you look back 2 graphs, right, it's odd. But since it starts facing up and it's going to end facing down, it's ending facing down, that means that you have a negative leading coefficient. Okay, so again, this is going to help us when it comes down to the actual graphing portion once we get to it in the next section, where we're filling in all the details in between, but at least we have the basics down. Okay, so thank you for tuning in, and I'll talk to you guys later.